Okay, so welcome everyone. Thanks all for being here. And today, so for this first probability and city online seminar of the semester, it's our great pleasure to have Andrew Han from Colombia. We'll be talking about Airy edge fluctuations in random matrix sums. Okay. Well.
Okay. Yeah, so thanks a lot for letting me talk about this work. So basically what I'll talk about is a new integrable probability approach to studying local edge fluctuations in certain additive random matrix models. So the goal will be to give you a sort of outline of the approach, what the new elements are in this approach, and hopefully I can convey that by the end. So let me first define the model that we'll look at. So we'll say that an n by n random Hermitian matrix A is unitarily invariant if the distribution of A is invariant or doesn't change under conjugation by unitaries. Okay. So the classical example of this is given by the Gaussian unitary ensemble. For us, we'll be studying sort of the extremal measures in this class. Those are given by random Hermitian A where the eigenvalues are deterministic. Okay, so we'll be looking at an independent set of unitarily invariant matrices A1 through AK with deterministic eigenvalues. Another way you can view these matrices is as given by a conjugation of a deterministic diagonal matrix lambda with real entries by a Haar unitary u sub I. Okay. So this is the model. And what we'll be interested in is studying the large n limit of the eigenvalues of the sum of the AIs. Okay, and so we'll be, we'll assume that the eigenvalues of these A sub i's are converging in some sense. And so to make more precise the notion or the limit regime that we'll be studying, I'll need to define for you the spectral measure. So we'll say that given X, a random matrix X, with possibly random eigenvalues x1 through xn, that the spectral measure of X, denoted by mu sub X, is just an average over delta masses sitting at each of the positions of the eigenvalues x sub I. Okay. So the picture that you could have in mind is, if you have eigenvalues sitting at -2, 1, and 2, then we just think of a histogram where sitting on top of each of the eigenvalue positions is just a mass of 1/3. Okay, so any questions about the setup so far? Okay. So before I get into a statement of our local fluctuation theorems, I want to give a quick limit shape result. So this is, I think, fairly important to say. And this is due to Voiculescu back in '91. So under the assumption that the spectral measures of these A sub i's converge weakly to some deterministic probability measure mu I. So recall these A sub i's have deterministic eigenvalues. So these mu AIs, the spectral measures, are just deterministic measures. So if these deterministic measures converge weakly to some mu sub I as n tends to infinity for each I, then the spectral measure of the sum of the AIs, so now this sum is going to be a random, this spectral measure here is going to be random, converges weakly in probability as n tends to infinity to some measure, which I've denoted here as mu1 box plus, mu2 box plus, etc. And this box plus here is the free additive convolution. Okay, so for those of you who don't know what the free additive convolution is, you could just think of this as some binary operation on which is commutative and associative on probability measures. And so what this theorem is saying is that the operation of random matrix sums in the limit ends up giving you some limit shape which also preserves this additive structure via the free additive convolution. Okay, so here's a sort of example, picture example of what the free convolution looks like in this specific case. So if you choose mu A1 to converge to the Rademacher distribution, which just has a mass of 1/2 sitting on top of -1 and 1, so mu1. And you have mu a2 weakly converging to the arcsine law, mu2, then the free convolution of mu1 and mu2 is the limit of the spectral measure of a1 plus a2, and it looks like this. So you can see that it sort of has this sort of regularizing effect in some sense. So any questions about this setup and background? Okay. So one can say more about fluctuations from this limit shape. So the global fluctuations are known to be Gaussian. I'm not going to state any precise results here, but I just want to point out that this can be done by second order freeness, and this was developed by Kalan, Mingo, Schneati, and Speicher. And there are also some more recent approaches using multivariate Bessel generating functions due to Gorin and Sun. So these sorts of questions have been answered. For us, we'll be interested now in questions about, the edge of this limit shape. And so let me transition now to the main results that we'll be talking about. So we'll be describing an approach to talk about the behavior locally at the edge of these additive random matrix models as n tends to infinity. And this question is pretty broad. So depending on what the a sub i's converge to, they could converge to some pretty pathological measures, and depending on that, they might have, extremely non-universal edge behaviors. So what we'll focus on is a particular setting in which the Airy point process arises at the edge of these additive random matrix models. So let me quickly recall that the Airy point process is the limiting point process which appears at the edge of the spectrum of the GUE. Okay. And so here's the cartoonish image of what we'll do. So we know by Voiculescu's theorem that these additive random matrix models have some sort of limit shape. We'll want to zoom in at the right edge of the spectrum at a scale such that we can see the individual eigenvalues and describe what that point process is. We'll particularly focus on a regime where the Airy point process will appear. So here are some things that we already know. So the GUE, the reason why the Airy point process should appear in sort of a fairly broad regime is that it's this universal object, and the universality of the Airy point process has been established in random matrix theory and models outside of random matrix theory. But here's a couple results within random matrix theory. We have that in the class of Wigner matrices, edge universality was established by Soshnikov back in '99 using a method of high moments, large moments. If you don't know what a Wigner matrix is, basically just think some n by n matrix with IID entries that are centered and some conditions on the variance. So you might want to scale it as 1 over square root of n. There are more methods since Soshnikov establishing edge universality. Tao Wu established this using some ideas based on the Lindenberg exchange method adapted to the random matrix setting. And there are various other methods as well. There's a dynamical approach using Dyson-Brownian motion. And this method was used to establish universality in the bulk by Erdős, Pichet, Ramirez, Schlein, Yao. And these ideas should also be able to extend to the edge as well. For the additive models, a lot less is known. So in the particular case where we take random matrices A and B, Hermitian, where A is GUE now, it turns out that the eigenvalues of this additive random matrix model are determinantal. And so the correlation kernel for these models were computed by Johansson back in 2001, building on some of the ideas of Brazen and Hakami from '96. Using these correlation kernels, various authors were able to establish local edge asymptotics under a variety of regimes where you can take B to B, under various assumptions on B, local edge asymptotics were obtained for this additive model. So more generally, you can relax this assumption that A is GUE to A being Wigner. And so if B is suitably regular enough, Lee and Schnelli were able to establish local edge universality. But more generally, for more general A and B, these sorts of local edge results don't really exist. So there is an exception here. Bao, Erdős, and Schnelli were able to show rigidity at almost optimal scale under assumptions that the edge of A and B behave regular enough. But still, there's no, beyond this case where A is Wigner, there are no results that are saying, okay, we have the Airy point process, which appears for, general A and B. One sort of exception, okay, so in another direction, Che and Landon were able to establish bulk universality for these additive random matrix models, just assuming mild regularity assumptions on A and B. So this is sort of a remarkable result in that, amidst all these additive random matrix models, they were able to show local bulk universality. And so there isn't an analog of this for the edge. And this was part of the motivation for this work. Are there any questions before I move on? Okay, to state our results, I'll first need to give you this notion of convergence now. So we want something stronger than weak convergence. So we'll say that a sequence of measures mu n, probability measures mu n, converges with its support to a probability measure mu. If as n tends to infinity, we have weak convergence. And also the support of mu n convergence in the sense of Hausdorff distance to the support of mu. Or the Hausdorff distance of the support of mu n and support of mu converges to 0. So this assumption here is just to ensure that we don't have any outlier eigenvalues. We just want, so mu n you can think of as being these empirical measures, and we want the eigenvalues to concentrate near the support of mu, the limiting measure. Okay, so the regime that we'll consider first is where the matrices A1 through AK are IID. So under this assumption, we're able to show the following. So given mu, a probability measure which is compactly supported, there's going to be an explicit constant tau mu, such that if if k, the number of summands, is greater than or equal to tau mu, and the spectral measures of the AIs converge with its support to mu, weakly as n tends to infinity. So this weakly shouldn't be there, just mu AI converges with its support to mu. Then the eigenvalues of the sum of the AIs, which we'll denote by these x's, converges upon rescaling by explicit constants given here by just written here as math factor E and math factor V to the Airy point process. So in other words, what we're saying is, okay, well, if we take enough sums of these IID matrices, here k is some fixed number, but it just has to be large enough, then we should see the Airy point process. This explicit constant here is going to be given in terms of mu through its Cauchy transform, by the way. I don't think it'll be super enlightening to see the formula. What I do want to say, though, is that you might ask, okay, so is it actually relevant that tau mu depends on mu? As in, do we really see the Airy point process only when k is larger than some constant depending on mu? And this is important. So you can, if you give me any k, so say k equals 100, I can find you a bad enough measure mu such that if I take IID sums A1 up to A100, then this, there won't be an Airy point process at the edge. So there isn't a rigorous proof of this statement at the moment, but one can see this just by looking at the limiting distribution, the limiting measure, and see that it doesn't have square root edge decay. So this is sort of indicative that you wouldn't see the Airy point process there. So the assumption that tau mu depends on mu, or having this threshold tau mu depending on mu is important, but the tau mu that we have is not optimal. So meaning, there's some minimal k. So given mu, there's some minimal k such that you would expect to see the Airy point process by summing enough of these AIs. And this tau mu gives you a sort of upper bound on what that k should be. But our tau mu is not optimal. Hopefully that makes sense. So an example is if mu is the Rademacher distribution, then we expect that the minimal k should be given by 3. So one can check this. I mean, if you want to know the details, you can ask me after. And our tau mu is something like 64. So this gives you a sense of the non-optimality. So if we were to take the AIs to be non-IID, we do also have results in this case as well. For that, we need some assumptions, technical assumptions on the limiting measures. So if you say look at the sum of A1 and A2, then under some assumptions on the limiting measure of mu A1 and the limiting measures of mu A2, we're able to show or establish that there's the Airy point process again. And for this, these assumptions are again somewhat restrictive, but we're able to show that for certain Jacobi measures with the right power law decays, that we do indeed have the Airy point process again. And another setting in which we can establish convergence to this Airy point process is certain quantized analogues of these random matrix models, where the random matrices, unitarily invariant Hermitian random matrices, are replaced by representations of the unitary group, and eigenvalues are replaced by signatures, which correspond to irreducible representations of the unitary group. Okay, so we have these results which establish that the Airy point process appears under certain assumptions at the edge of these additive random matrix models. What I want to point out is that our method, we believe that it can access other edge behavior as well. So if you might be able to as well treat cases where you have some outlier eigenvalues or other interesting regimes, and this is subject of work that we're of ongoing work. Okay. So let me pause here, see if there are any questions. Okay, so let me first explain why.
There's one question in the chat. I can read it to you if you. So Anthony Noriega, he says, is there any relation between the variability of xi minus e and the magnitude of d?
Sorry, you broke out for a second.
So the question is there any relation between the variability of xi minus e and the magnitude of d?
The magnitude of d?
It's not supposed to be I think that's a v. He means probably.
I see. So e and v here should just be constant order. And actually, so the I didn't want to write this out, but e here and v here should depend on n, but they should be converging to some constants in the limit as n tends to infinity. Any other questions? Okay. So what I'll do is quickly just explain why you might expect increasing k to have a regularizing effect. So for that, I just have this heuristic here. So let's consider instead keeping n fixed and sending k to infinity. So think of keeping the matrix size fixed, but allowing the number of IID copies, to increase. So if we do that, you can apply ordinary multivariate central limit theorem to the entries of the AIs. And you'll find that upon recentering these matrices by some scalar matrix and rescaling, that this should converge to some Gaussian matrix. And so Gorin and Sun in their appendix show that compute exactly what the covariances of this of the entries of this matrix are given by. And they identify it with something called the traceless GUE. And so here on the left-hand side, we just have some constant. We have the matrix size n divided by n squared minus 1 times the variance of mu a1. And inside here, we have yn, which is a GUE matrix, subtracted out by a random scalar matrix here, given by 1 over n trace yn. So now if you send n to infinity, the matrix size, this part here will end up being negligible asymptotically. And so you have the heuristic that the sum of the AIs is approximately some scalar matrix plus a scalar times the GUE. So what this suggests is that for large K and N, you should expect the eigenvalues of the sum of the AIs to look roughly like a GUE up to centering and rescaling. And so the regime that we considered was K being finite and N being sent to infinity, but the point of this heuristic is just to suggest or show to you that, or suggest at least to you, that as you increase K, you should expect the model to approach the GUE in some way. Okay, so this is just to give you a sense of why that result makes any sense. So next, I'll get into some of the ideas behind how you prove these results. So the basic idea behind it is to take high moments, large enough moments that you're probing basically just the largest eigenvalues. And the key new input to this approach is that we obtain moment formulas for these additive models, which are analyzable. And the way we obtain them is through certain generating functions and a notion of supersymmetric lifts, which I'll try to explain to you. So before I get into how you get these sorts of moment formulas, I want to explain, okay, given moment formulas, how do you show that the Airy point process or convergence to the Airy point process? So for that, let's assume that we have eigenvalues x1 through xn, and let's assume that we know that under this rescaling, under this scaling, that the eigenvalues converge to the Airy point process. Okay, so we assume we have some explicit constants, math factor e and math factor v, such that this n to the 2/3 xi minus e over v converges to the Airy point process. So if we know this, then we have the following. So if we take the expectation of these exponential moments, where we have this n to the 2/3 c inside the exponent, and we denote by a1, a2 a copy of the Airy point process, then this expectation should behave asymptotically like some e to the n to the 2/3 ce, the edge, times an expectation over the exponential moments of the Airy point process. To see this, you basically can just write this as being approximately a sub I and plug in to the left-hand side. There's a more general statement you can make for joint exponential moments, which tells you how these joint exponential moments should behave asymptotically in terms of the joint exponential moments of the Airy point process. And so, okay, so if you have convergence to the Airy point process, you have some, this implies some statement about the asymptotic behavior of joint exponential moments. And the point is you could also go backwards. So if you have this sort of description of the asymptotic behavior of the joint exponential moments, then this implies convergence to the Airy point process. So this is the general, idea behind how you might use moment formulas to extract edge behavior. So now for the remainder of this talk, I'm just going to focus entirely on how one might get these sort of moment formulas for these additive random matrix models. Okay, so to describe this, let me start with a simple analog in classical probability. So let's say we have a random variable x with Laplace transform phi x of z. Okay, and let's say it's defined in some neighborhood of 0, z being z in some neighborhood of 0. So if I want the moments of this random variable x, all I need to do is differentiate phi x and evaluate, take the derivative at 0. So if I let dk be the kth order derivative of z, then expectation x to the k is just dk phi x of z evaluated at z equals 0. Okay, so from here, I can re-express this as a contour integral. So we can write this as k factorial over 2 pi I integral over phi xz divided by z to the k plus 1 dz. And this is just by residue theorem. Right? So we can Taylor expand this thing about 0. And this is how you extract out the kth derivative. So the point of this simple example is to say, okay, well, if we have the Laplace, a suitable representation for the Laplace transform of x, then we can obtain some contour integral representation for the moments of x. And if we want to take some sort of asymptotics of this x to the k, then we can try to use these integral formulas, perhaps use steepest descent to say something about the behavior of these moments asymptotically. That's the simple example here. And so what we want to do is have a similar format in our model. So our approach, we'll do it in 3 steps. So first, we'll want to find an appropriate notion of generating functions for our models. So what is the analog of the Laplace transform for these additive random matrix models? The second thing that we'll do is find some appropriate set of operators and relate the moments of our random matrices with these operators, right? So this is sort of corresponding to this step here. We want to find some action of these operators on our generating functions, which relates it to the moments of our additive random matrix models. And the third step that we'll do corresponds to this equality here. So we'll want to find analyzable formulas for our moments through this description of operators on generating functions. So this will be sort of the 3 steps which will obtain these moments. So any questions about this general approach? Okay. So let's start by finding the right analog of the Laplace transform. So let me just tell you what it is in our setting. So let's say x is just some vector of weakly decreasing real numbers. The multivariate Bessel function, which is indexed by this x, is then just denoted here by mathcal b sub x, z1 through zn. And we can define it as some alternate, some determinant of e to the xi zj divided by the van der Maan of the zi's. This might not be so illuminating. So this is proportional. Alternatively, this is proportional by the Harish-Chandra-Itzikson-Zubair formula to an integral over the Haar unitary, over the Haar measure on the unitary group of e to the trace xu zu star. So here, x is a diagonal matrix of the x's, and z is a diagonal matrix of these z's. Alternatively, another way these functions have been referred to in the literature is as continual Schur functions. This is because they can be realized as certain limits of the Schur functions, where the Schur functions are, given by S lambda, where lambda is some partition or some weakly decreasing sequence of integers, and somehow you want to, come up with a continuous analog where instead of weakly decreasing integers, you have weakly decreasing real numbers. Okay, so our notion of Laplace transform in this setting will be given by a certain expectation over these multivariate Bessel functions. So if you have a random Hermitian matrix X with random eigenvalues little x, then we say that phi x z1 through zn is the multivariate Bessel generating function of x, or just mbgf if the expectation, if phi x is equal to an expectation over these normalized Bessel functions. Okay, so this expectation is over the eigenvalues x, and so this is the random part here. Okay. So before I give some examples of why this is a good notion of generating function in our setting, and some examples of MBGFs in familiar cases, let me just say that this object was used by Gorin and Sun to show global fluctuations for random matrices. They studied more than just additive models. They considered these products of unitarily invariant random matrices, and similar ideas have been used to study discrete models. This was done by Bufetov and Gorin in their papers from 2015 and 2018. Okay, so let me give you some examples. So the first example that I'll give tells you that the MBGFs have this factoring property, which is analogous to the factoring property of Laplace transforms for sums of independent random variables. So if you have A, B are independent random unitarily invariant Hermitian matrices, then the sum of A and B, the MBGF of this, is just going to be equal to the product of the MBGFs of A and B. Okay, so that's nice. This gives you some sense that this is a reasonable generating function to consider in our setting. The second example that I want to give is an explicit formula for the GUE, an explicit formula for the MBGF of the GUE. So if x is GUE, then phi x will be equal to just a product over I equals 1 to n of e to the zi squared over 2. So that's a nice form, and this also, it's also clear from here that if we take n equals 1, this properly degenerates to the Laplace transform of a standard normal random variable. And the final example I want to give is that if A has deterministic eigenvalues, A1 through AN, the setting we care about, then the MBGF of A is just going to be given by the normalized Bessel generating function indexed by the eigenvalues A. And this is just because you had this expectation here, and if the eigenvalues are deterministic, you're taking an expectation over a constant thing. Okay. So the next thing that we want to do is find the right analog of find sort of the operators in this setting which give you moments. So in the classical probability example that I gave you, we had these derivative operators that give you the kth order moments of x. So here the sort of analog of the derivative of z, kth order derivative of z, is given by this operator here, which you just take a sum of the kth order derivatives of the zi's and conjugate by a Vandermonde. So this will give you moments of these random matrix models. But for our setting, it's more convenient to consider the exponential moments. And so for that, we replace this derivative term on the inside by shift operators. So TCZI just takes a function f and shifts the ith input by c. And if we consider this operator, then it turns out that applying dc to an MBGF to the MBGF of x and evaluating at zi equals 0 gives you just the expectation over these exponential moments. Okay, so just take this at face value. The point here is that we've related the exponential moments of x to some action of an operator on its MBGF, on its generating function. So now our goal is to use this representation to come up with some reasonable formulas for the exponential moments. And so that's the next main result that I want to say. So using these operators, we have the following. So suppose you have a function phi tilde x. So this function is going to be a function in n+2 variables. This backslash here is not a quotient. It's dividing, it's sort of separating these two variables. And the reason for this notation is due to existing notation, which for another class of functions, which are closely related to these. But point is, okay, we have two sets of variables, z1 through zn+1 and w, and phi tilde will be symmetric in the z's, but not all the variables. And we require that if we take phi tilde x and set zn+1 to be equal to w, then these two variables cancel, and we end up with phi x z1 through zn. So this is a cancellation property. So if we have the existence of such a lift of phi x, then the exponential moments of x are given by this contour integral formula. So here, this motivates us to find a good representation for these phi tilde x's for our models. And I'll get to that in a moment, but let me just say that these phi tilde x's we refer to as supersymmetric lifts of phi x. So the reason why we call them supersymmetric lifts, hopefully I can, give you some justification for this towards the end. But for now, let me just give you some examples. So any questions so far about this?
Can I ask a question?
Yeah.
So if I'm just looking at this formula, is your assumption telling me anything about what phi tilde is when the zi's are all different from w?
No, it's not.
Okay.
So here phi tilde x should be analytic in these zi's.
Oh, okay.
But you're still right in that it turns out that it won't be unique.
Okay, but at least there's some kind of, because you're integrating it over something where your assumption is not, like this integral is over places where they're not the same. So.
Yeah. That's right. But yeah, so these phi tilde x's should be analytic in the zi's, in the z's and the w. And we'll see. I'll try to convince you. Okay, so maybe I won't have time to convince you, but there are certain natural choices of what these lifts should be in our models. Okay, so here's an example. So let's say phi x, your MBGF, has this multiplicative form. So it's a product over the zi's of f of zi. So for example, the GUE had this form where f of x was given by e to the x squared. So in this case, you can write down a supersymmetric lift of phi x, and it's pretty simple. So you just take, all right, so you have n+1 variables of the z's and a w. What you just do is you take a product over f of zi and divide by f of w. And you can see that if I take w equals en+1, then these two just cancel. So in the case where phi x is multiplicative, it's pretty easy to find a lift. And so if you apply our theorem, our proposition to this case, so you have this formula for your exponential moments, then you just take phi tilde x, replace it by this formula, and you end up getting f of z plus 1 by f of z. So here it turns out that f of 0 has to equal 1. This just comes from the fact that if you look at our MBGF and evaluate it at all the zi's being equal to 0, this should be 1. But yeah, this is what the formula reduces to in this multiplicative case. It turns out that this case you could have come up with this as a corollary of some formulas for observables that Bourdieu and Corwin have in their work on McDonald processes. But for more general non-multiplicative forms, this sort of theorem wasn't known. Okay, so we have a formula for these multiplicative models. What we care about are these additive random matrix models. So in general, it's the case that it's hard to compute these phi tildes. However, we do have the following nice property, that they behave well under multiplication. So if you have lifts phi tilde A and phi tilde B of phi A and phi B, and it turns out that phi tilde A plus B is just going to factor into the lifts of phi A and phi B. Okay, and so this comes from the fact that phi A plus B factors into phi A and phi B, and this notion of taking supersymmetric lifts behaves well under products. Okay, so using this, so from this property here, what this suggests is that it just suffices to find a supersymmetric lift, a representation for a supersymmetric lift of these multivariate Bessel functions, right? So this is because, we had that the MBGF of these deterministic, of these Hermitian matrices with deterministic eigenvalues is just given by multivariate Bessel functions. And so if we can find lifts of those functions, we can take product of these lifts in order to study these additive models. Does that make sense, or should I elaborate on that a little more? Okay, so basically basically what I'm saying is that for these additive random matrix models, in order to study them, it suffices to find a good representation for supersymmetric lifts of these multivariate Bessel functions. And so we were able to do this. So we were able to show that there's some explicit function b tilde a, z1 through zn plus 1, w, given by this sort of big formula here, which is the supersymmetric lift of these multivariate Bessel functions. Okay, so this is pretty mysterious. So let me say a word on what this sort of means. So it turns out that, or where we came up with this. So it turns out that these lifts are certain limits of the so-called supersymmetric Schur functions. And so supersymmetric Schur functions are, you can view them as certain lifts of Schur functions which satisfy this cancellation property. And they come up in, as characters of irreducible representations of these sort of super analogues of GLN. And so these objects sort of mysteriously show up in our formulas through this cancellation law. And this is where we came up with the idea of, okay, well, if we have this cancellation property for the supersymmetric Schur functions, maybe this is what we need. Maybe we just need to take the appropriate limits of these supersymmetric Schur functions to get the right lifts for the multivariate Bessel functions. This was where that connection was made. And where do we get suitable representations for these supersymmetric Schur functions? Well, it turns out there's a paper of Mons and van der Joet back in 2003 where they found determinantal formulas for them. And so this theorem here really comes from.
Question. So the use of the term supersymmetric, this often means taking a sort of dual specialization.
Yeah.
Is that what this is being used for here? This is a limit of this sort of dual specialization in one variable and the standard specializations in the other?
Yeah, so that's certainly the case. So what you can do is you can look at the algebra of symmetric functions and consider taking, a specialization which gives you some alpha variables and some beta variables. And if you view these beta, if you look at these beta variables and take them to be negative, then they'll cancel with the alpha variables. And this is where the connection between that and these supersymmetric functions come from. Yeah, hopefully that answers your question. Yeah, so So this is where these objects sort of came from, and this is why we choose to call it supersymmetric lifts. But now, okay, we have some determinantal expression for this. What can you do with it? So I'm not going to write it down, but it turns out you can come up with some analyzable contour integral formulas. So now, you plug this into your moment formula. You can rewrite this determinant in terms of some nice contour integrals and take asymptotics and steepest descent. And this is how you can access these local edge results. And it turns out, so Alex asked before, well, or I guess it was sort of suggested that these supersymmetric lifts are not unique. And it turns out that we do use this property. So we use the fact that you have some freedom in choice of lift. And so we find these analyzable formulas for a family which generalizes these lifts. Okay, so that's pretty much all I wanted to say. So let me just give a quick summary. So we outlined an integrable probability approach to study the edge asymptotics in these additive random matrix models with unitarily invariant symmetry. And in particular, we focused on a regime where the Airy point process appears. Although we believe that this method should really extend to other settings as well. And so the key idea behind this approach, the key new input was these moment formulas which relate moments of these additive random matrix models to certain lifts of their generating functions, and being able to find reasonable expressions for these lifts as well. And in there was some mysterious connection with these supersymmetric Schur functions, which I think should still there's a lot of questions there as to why these things arise. So that's hopefully something that we can look into further in the future. That's all I want to say. Thanks for your attention.
Let's think, Andrew. More questions?
I have a couple. So you found this regime that this limit converges to the Airy point process, right?
Yep.
So do you have any notion of the behavior in the bulk?
No. So this method is pretty ill-suited for the bulk. At least there would have to be several new ideas to access the bulk. And the reason for this is that we're really using a moment-based approach where here taking a high enough sort of power is going to just allow the largest eigenvalues to dominate. So sort of the crux of that.
Okay, and if this converges to the Airy point process in the limit, do you have any, because we know that, for example, in GUE, we know that the largest eigenvalue converges has this Tracy-Widom distribution. Do you know that if this happens in this case, well, you have this limit convergence in the edges, maybe the largest, do you know anything about the largest eigenvalue or the distribution of the largest eigenvalue in this case?
Well, so we're able to show convergence of the largest particles to the Airy point process, and so this gives you the convergence of the largest particle to Tracy-Widom 2.
Okay.
Yeah. In particular.
Okay. Thank you.
Yeah. Thanks.
More questions? No one? Okay. Let's thank Andrew again then.
Thank you.
Thank you.